I'm John Fazio. I'm with the Northwest Power and Conservation Council. And the council is an interstate compact created by Congress in 1980. It's a compact among the 4 Northwest states, Oregon, Washington, Idaho, and Montana, with 3 functions. The first function is to develop a fish and wildlife program to mitigate, protect, and enhance the fish and wildlife that were affected by the building of the hydroelectric system. Second function is to develop a power plan for the region to make sure that we provide an adequate, efficient, and economical power supply. And the third function is to do all of this in a public forum. Many of you have probably heard of us before. I'm so pleased to make this presentation at the Bullitt Center because this is one of the best, if not the best, examples of what you can do with energy efficiency. And I've got to say that because, after all, conservation is our middle name, right? You've heard that before. Anyway, okay, so I have only one function today, and that is to try to give you a perspective on how climate change might affect the power supply in the Northwest. I'm a systems analyst for the council, and part of my job is to develop a computer program that simulates the operation of all the hydroelectric projects and all the power generators in the West Coast. And we do a lot of what-if studies. We run studies into the future. They're called Monte Carlo studies, where you pick a year and there's a lot of things that we don't understand. We don't know what will happen in the future. One of them is obviously temperature, how thermal resources will behave. You could have forced outages, water conditions, wind generation, solar generation. Those are all variables that we really don't know what's going to happen in a particular year. It's very difficult to base your planning on averages because in one year you may not get the average. So what we do is we run thousands of games or studies, simulations, and then we look at what happens across all of those games so that we can plan for sort of the expected observations and also for the extremes. So today what you're going to see is our analysis of a potential climate change scenario, just one. You've seen a picture of this, Columbia River Basin. Just some facts about the Columbia River Basin. The annual volume of water that goes through the system is about 136 million acre feet. 1 acre foot of water is the amount of water that would cover 1 acre of land at a depth of 1 foot. I don't know what it is in gallons, don't ask. 136 million acre feet pass through on average. In the lowest water year, it's about 60, and in the highest, it's about 200. So there's quite a range of variation year to year. The reservoirs in the US and in Canada can store only 40 million acre feet, or about 42 million acre feet of water. That's about 30% of an average runoff. So we can't control the river as much as we'd like to. Okay, about half of the storage is in Canada, and the other half is in the United States. So just some figures and facts about the Columbia River. What this chart shows is I have 80 years of historical natural flow data. This is the flow that you would see in the Columbia River if there were no dams, you know. And this chart starts in October, goes through September. We split a couple of the months. We split April and August because those are the shoulder months. And on the vertical scale, we have flow in thousands of, in cubic feet per second. Okay. Now these are monthly averages. So you can well imagine that the daily flows or the hourly flows will vary more than that. But I just wanted to give you a sense for the variation in the annual stream flows and in the shape of those annual stream flows. And at the very end here, we should get a black line. That's the average. Source of the data real quick. This analysis is based on the IPCC 4 studies. We don't have data on the IPCC 5 yet. This data, the studies that are run are using global circulation models. That data is unusable by us in our models. They have to be downscaled for the Northwest. And so the information that's important for us is temperature and precipitation and stream flows. So the summary of the downscale results, we've seen this already before, I'll just run through this really quickly, is that we expect that temperatures will increase in every month to some degree across the entire region, in some regions higher than others. The annual precipitation, we're uncertain about. We may get a little more, we may get a little less. but the likelihood is high that we're going to see a shift in stream flows. This chart is similar to the one that we had before. The black line is exactly the same as the one that was before, and that is the average of the 80 years of historical natural flows. The red line is how we expect that average to shift under this one particular climate change scenario. One of the things that happens is there's a shift. We have, and the scale is kind of rough here, but we see higher winter flows, we see lower summer flows, and we see that the peak of the flow is happening earlier. But the point is that it's dwarfed by the annual variation in, okay, there we go. So it's dwarfed by the annual variation in river flows. So you're not going to see a scientist go out to the river and measure the change in river flow and come back with the headline the next day that says, hey, we've proved climate change. You know, you're not, because these small changes occur over long periods of time, and the natural variation in conditions each year just blotted out. So it's kind of a signal-to-noise ratio. Does it mean that it's not happening? No, not at all. But it means that it's just difficult to detect. So what happens when temperature goes up in the Northwest? This chart shows a couple of things. It shows the months across the horizontal scale, and on the far right, the vertical axis, we have temperature in Fahrenheit, and the black line shows the expected, out of this one study, it's just one scenario, it shows the expected increase in monthly average temperatures. And you can see that the increase in temperature we expect is on the order of 2 to 3 degrees Fahrenheit, okay, Fahrenheit. On the other scale, the vertical scale, we show how the demand in the Northwest changes because of this change in temperature. We see that with higher temperatures in the winter, because that's our heating season, we actually have a lower demand. But the opposite happens in the summer. With higher temperatures, we get higher demand because air conditioners go on. So this will be interesting, because when we combine this effect with the effect of the shift in river flows, it's kind of like a double whammy in summer. It helps us in the winter, but it hurts us in the summer. So these are the results of our studies, the average results, and they show that this chart shows the average change in regulated flows. That's not natural flows, but the flows as they come through the dams in the Columbia River Basin. And this shows just the change in flow. We see that in the winter we get higher flows, which translates into more hydroelectric generation in the winter. And in the summer we're going to see lower flows, which translates into less hydroelectric generation. I have to remind you again that this is just one climate change scenario, and it's based on an old study, but the trends all seem to be the same. So we can convert this into generation, because our model does that. We get this pattern of more generation in the winter, less generation in the summer, and when we put it all together, which is my last slide, we get this summary of the effects of climate change, or at least this one scenario on climate change on the system, and that is, you can almost ignore the numbers. This is just illustrative only because it's old data, but look at the meters down here. In the winter, we expect that the generation will increase because we have more flows. At the same time, demand is going to go down, so that gives us more. It gives us a better situation. It gives us a more adequate supply. In the summer, the opposite happens, where we expect the generation to decrease because we have less water available, and we have a higher demand because the temperatures are higher, so it's the exact opposite. Now, how does this affect our power supply, our costs, and the adequacy of the system? Well, it turns out that the Northwest has always been, traditionally, a winter peaking region, meaning that our highest demand occurs in the winter. However, lately, because of increased air conditioner penetration and because of other economic factors, our summer demands have been growing and our winter demands have been decreasing somewhat. So we are approaching the state now where we are almost a double peak region. In Idaho, they are double peak because of irrigation demands. And so the effect of climate change is going to be to give us some help during the winter when we really don't need it, but it's going to decrease our available amount of hydroelectric generation during the summer at a time when both California demand is going to go up and also the Northwest demand is going to go up. And so the implications are that it will we'll have to look to other places to replace that energy, either in terms of more energy efficiency or other resources to make up that difference. And we hope that for the next power plan, which should come out in 2015 or so, that we will have newer data and more quantitative results of the impacts of climate change on adequacy and on the cost of electricity for the Northwest. And that's all I have.